Hello there. Man, the solution to this problem, it's honestly going to blow your mind. This is 1035 uncrossed lines. All right, this problem has 40 dislikes. Yeah. Don't like the problem until you complete it. All right. No, I can't do that. I can't. It's just not right. It's not right. It's not right. Okay. Jesus. All right. So you're given two integer arrays, nums1 and nums2. We write the integers of nums1 and nums2 in the order they are given on two separate horizontal lines. All right. So if you're given 1, 4, 2, for example, all right, 1 and a 4 and a 2 and 1 and a 2 and a 4. You write them like so. All right. On two separate horizontal lines. We may draw connecting lines, a straight line connecting two numbers, nums1 of I and nums2 j, such that nums1 of I and nums2 j are equal, and the line we draw does not intersect any other connecting non-horizontal line. So what the hell does that mean? Well, that means, right, that I could connect elements to each other from one horizontal line to the next if they're equal, right? So I could connect 1 to 1, I could connect 2 to 2, and I could connect 4 to 4. But this state would not be appropriate because there cannot be any intersections, right? So there's an intersection here, right? Because you see this line crosses over this line. So it is an issue, but I could draw the system like that, or another valid form is like this. But of course, given that constraint, we should already be thinking about the fact like, okay, if this problem has to do with drawing uncrossed lines, well, I can't just draw an infinite number of lines. I need to make an infinite number of lines. I can't just like draw every pair that is equal because there's going to be cases where it crosses. So how am I going to deal with the fact that sometimes there's crosses, and how do I find the optimal solution given that constraint? Note that a connecting line cannot intersect even at the endpoints. The number can only belong to one connecting line. Okay, interesting. So if you had a problem like this, right, where there were, let's just say for the sake of proving that point, what it's saying is you can't do this. Or this could be anything, actually. Let's say this was 4, 3. I am screwing up. 4, 3, like so, right? If I cannot do this, right? You say, well, there's no intersection here, right? Like these two lines obviously don't intersect, but if it helps you, you can think of it crossing through the whole item, right? And you see that they intersect here. But the point is, right? They can't. Every endpoint, every element, we're gonna call them endpoints from this point forward. I promise. Every endpoint can only connect to one other endpoint, right? There's two endpoints connecting to this endpoint, so that's an issue, right? All right. Return the maximum number of connecting lines we can draw in this way, right? So we're going to try to maximize the number of lines we can connect where each connection between endpoints, the elements are equal at each endpoints, but there's no intersecting lines. So we're going to have to be conscious of the fact, like, like there may be two things that are connected, but if they're far away, right? Like say there was a 2 over here and a 5 or something like that, right? You definitely don't want to do this. If you want to maximize the number of connecting lines you get in the system, these are just things to think about, right? I don't want to do this, right? Because now what does that do? Now that I do that, I can't connect any what? I can't connect these because there's an intersection, right? I can't connect these because there's an intersection. Right, I'm creating a lot of issues by forcing this line. And if anything, you notice, like, if I connect something at the top to something at the bottom, everything in between them are now stuck, right? All of these elements down here are now trapped, at least to the left, right? They could connect to something on the right, right? If there were more elements this way, this thing could connect going here. But now it's constrained to the left, right? Because I've kind of covered that whole system, right? I've just drew a line through. So there's no way that I can draw any line through this system in any way. Love you guys. All right. So with that said, let's do the example problem. So when we have 1, 4, and 2, and 1, 2, 4, the optimal solution is, well, there's 2, right? Because you could do 1 to 1, right? And then you could connect 2 to 2, and that would give you 2. Or you could connect 4 to 4, as it is given here, and that would also provide you with 2 connected lines. You know, that's obviously the solution. You can't do this, right? Because that would create an intersection. All right. Here's another one where it's not given the thingamajig. So let's take a look at this one. Maybe that'll provide us with a little bit more intuition about how this problem is solved. Sometimes it can be hard when there's a graphic given and the problem's very simple to try to have any sort of intuition about the solution, because it just gives it to you too straightforward that it doesn't even really give you the opportunity to think about it, right? So nums 1 is 2, 5, 1, 2, 5. Okay, 2, 5, 1, 2, 5. And nums 2 is 10, 5, 2, 1, 5, 2. So nums 2 is longer. Is that right? 3, 6, 5. Okay. 3, 6, 5. 10, 5, 2, 1, 5, 2. 2, 5, 1, 2, 5. Sorry. There is a little bit of my stupid face in the way. So that makes sense, right? Like, you just draw them out. Does that make sense? Literally just say the problem. But always write down the problem, right? And then ensure that you wrote it down correctly. Because the last thing you want to do is mistakenly put a 5 when you're supposed to put a 4 or something, and then you solve the whole problem, and then it's wrong, and then, you know, maybe you look like a fool. I don't know. Double check. Okay, so, you know, when I look at this problem, well, how am I going to systematically do this so that I can find that the solution is 3? Well, I can start connecting things, right? And you can see what the answer is. But this is always one of the biggest issues when you solve these problems, right? Because it's like, well, like, somehow deep in my brain, there's a neural network that determines how this is solved, and I can just do it. But I can't think of the way that I would systematically write code to do it, right? Like, I'm just looking at this, I'm like, oh, I'll connect this to this, and this to this, and this to this. Boom, that's 3. Done. But it's like, a computer doesn't work in that fashion, right? Like, how does a computer make that computation, right? There has to be something that's, like, procedural in order to do this. Right? Because there's another solution, right? I could also do this. Or I could do this. Right? Or I could do this. So there's a lot of solutions here to even consider. So I guess a systematic way of doing this is to think about, like, if I connect 2 things, if I connect 2 nodes to each other, if I connect 2 endpoints to each other, what is the best solution I can get? At any 2 endpoints, what's the best solution I can get? Right? So what I can do systematically to do this, and since nums length and nums2 length is only 500, for each endpoint, I can check its connection to another endpoint and figure out what the optimal solution would be there. Now, from here to here, they can't connect, right? Because they're not equal. So the answer would be just 0. From here to here, they're not equal, right? So its best solution would be whatever comes before, which is also 0. I can connect this to this. Now these can connect. So from here to here, I can connect them and get 1 point. I can't connect here. I can't connect here. Maybe this isn't the best way of going about this. So how do you systematically then do this, right? Because you can walk through, but what you should really do is think about maybe in a general case what the consequences are of connecting or not connecting an endpoint. Okay, so we're going to look at all the endpoints, right? And we can definitely do that. We can look at all pairs of endpoints, and we'll see if we can look at all pairs of endpoints and make some statement about what that would mean for the solution if we were to connect these endpoints, if we can connect these endpoints, if we can't connect these endpoints, etc. Okay, so generally what I'm going to do is I'm going to draw these endpoints like so. So let's say I draw a few endpoints in the system. Right? I'm not making any statement about these endpoints. And then we have the node I and the node J. And we're trying to see what the consequences are if we connect node I to node J. And let's say that this is representing nums1 and this is representing nums2. All right. Now, if nums1 of I equals nums2 of J. If we try to connect these things to one another, right, meaning that this connection could happen, what would that do to our total score? Well, let's say that we have some dynamic programming array, right, called best. And best of ij equals, we'll make it blue. Let's say best of ij equals the most points we'd get connecting up to I and J. So that's the best solution up to any point, right? So like the B of 1 would be the best solution up to this point going left, right? So it's the best solution from the left up to a point, right? So if we can connect I to J, we'd say, well, the best of ij is what then? If we can connect them, we'd get another point. We'd get 1 point, and then it would be the solution of what? Well, there's really two ways that we could do this, right? We could get the maximum. If we think about this kind of, well, there's two things we can do, right? If we connect them to each other, then we have to use the best system over here, right? So that would be, say, the max. So I'm trying to make this look nice. And I'm not explaining this well at all today. The maximum of, well, I can get 1 point, and then it's the best solution from, well, what is this? This is I minus 1, right? And this is J minus 1. So I can get the best solution from I minus 1, J minus 1. Or, right, I'm going to make me smaller because I'm in the way. Or I can decide that, you know, I don't want to use I of J. So if I don't want to use I of J, then I can just take this solution like so. So the solution where I don't make this connection, right? Because if I make this connection, I cannot make this connect. Like if I make the green connection, then this red connection can't exist, right? So if I decide not to make the green connection, I can see if this connection exists, so I can use the best system here. And we'll call that the best from I minus 1 J, right? So I can take either of those solutions if I were to connect them, right? Sort of. I mean, that was kind of my initial thought. But if you think about it, right, if the only thing that happens if I connect I to J is that this connection can't exist anymore, right? The only connection that can exist if I connect I to J is this one. So since that connection can't exist, adding I to J isn't going to change the score, right? Like if this connection exists and then I connect I to J, it's not going to decrease my score at all. So I don't need to think about the max of anything, right? If I connect I to J, it'll only subtract 1 from the optimal solution up to this point where I minus 1 connects to J. So I might as well just not consider it because it would have the same value. Okay? But this is the case where these things are equal. What if they're not equal? Right? What if I and j are not equal to each other? So I'm going to make it, I'm going to say else, right? So if they're not equal, what would b of ij be in that case? Well, if they're not equal to each other, I don't get 1 point because I'm not connecting them. But if they're not equal, well, I have two choices for my optimal solution, right? I can either connect them to each other here. I can see what the optimal solution is here. In this case, so what I'm saying is in this whole system, right? So I exclude this j, and I say, okay, since I can't connect to you, maybe I can connect to you. So what's the optimal situation where we connect to each other? Here, right? And I've already solved that. Or let's say we've already solved that, right? So I can do that, which would be what? That would be b of ij minus 1. So let's move things down a little bit. Let's actually, this isn't. So there's two things I can do, right? I can choose to go to this node here. So that would be the maximum of this system. So let's make these things all colored better. So we'll use a highlighter. We'll say this is the green system. Or we could use the red system here. Right? So I could use that system, which is b of I j minus 1. So since they don't connect to each other, it's not going to add to my score. So I'll just say, okay, what's the best of the thing that comes before? Right? But this is going to be the max of either that or put max on one line. What's the other thing I can do? So if I connect these to each other, what am I losing? Well, now I can't connect, right? I can't connect these two to each other, right? So if I try to say what's the best of connecting these, if I make that choice that I'm going to connect these or try to connect these, right? Now these two can't connect to each other. So I can either try to connect these together and see what that best solution is, or I can try to connect these together and see what that best solution is, right? So that would be b of I minus 1 j, okay? And that would correspond to this system here. So that's about as good as it gets. Makes absolutely no sense at all. No. So the idea is generally, right, in this problem, and this is the recurrence relationship, is it's dynamic programming because it's kind of obvious that it's like, well, if I connect these things, I need to know what the best solution would be everywhere else, right? So if I just say, okay, if I connect these things, what's the best solution to the left, right? So I need to keep track of the best solutions to the left. That way, when I find new connections, I can figure out what the implication is in terms of the total number of connections that can be created, right? So the idea really is where it's like, if I have a set of nodes, right? If I have these set of nodes, you know, if I have a set of two nodes like this, or let's say three nodes, if I connect these two, then this can't occur. Right? And vice versa, if I connect these two, then this can't occur. Ugh. If I connect these two, then this can't occur. Right? So either way, if these are the two things that I can do. So one thing that's very common with dynamic programming is saying, like, what are the things that I can do, right? There's two universes. There's a universe where I try to connect these two to each other, which means that this can't happen, right? So if I do that, I know the implication. So I can either try to do this or I can try to do this. And then I just say, what's the maximum, right? So that's all I'm doing here, right? If they can connect, then there's no difference, right? If we're talking about something like this where, well, if they can connect to each other, so this is a green line, then it's only going to subtract as most 1. But if they can't connect, then I might lose points if I try to connect one or try to connect the other, right? So that's the general idea behind this problem. This is a very tricky problem. And honestly, when I solved it, I was like 70% sure that it was actually correct, and then the auto grader said yes. So this is definitely one of the more tricky mediums. I'd even consider this maybe a hard, but that's the idea. So let's go ahead and code in this relationship. Okay, so what I'm going to do is move me so I can move this. So let's make this small so that I can use it as like a reference, because I'm going to forget everything that's in it in about 5 seconds. So we need to think about how we're going to represent stuff. So for this B array, be real. For this B array, let's just use a default dict. That way we don't have to think about like, what if we go too far left? Like when we look at the first value, there's a value before. It's just easier to use a default dict. So we'll create a default dict, and the default value will be 0, because that would be the score of nothing, right? If things are disconnected, or you can't make them connected, if you can't connect them, then the default score would be 0, so that seems pretty intuitive. And then let's look at each I in num1. So we'll look at each endpoint in range length of nums1. And then we'll look at each endpoint in range length of nums2. Okay? And then we just ask this question, right? We say, okay, B, if they're equal, so if nums of I, nums1 of I equals nums2 of j, then we just say that B of ij equals 1 plus B of I minus 1, j minus 1. Okay, so B of ij equals 1 plus B of I minus 1, j minus 1. Is that right? Seems weird now. So if they connect, then yeah, okay. So we can put that on one line because we're just so savvy. Otherwise, they're not equal, so then we have to run through this example. Well, then I can try to connect them diagonally, or I can try to use the previous element. So I'd say B of ij equals the max of B of I minus 1 j, which is saying I'm using the previous element, or B of I j minus 1. And then at the end, you just return B of, well, the endpoint, right? Because the maximum solution will be the thing at the very end, okay? So that would just be B of length of nums, or I think I and j will have those values at the end. Kind of messy, but it should be fine. Let's print B. Probably messed this up because I'm an idiot. But, you know, so it goes. I don't know, so it should be this 2 value, which is 2. What if I just did ij? I could do the length of nums 1 minus 1, length of nums 2 minus 1, right? But I don't feel like doing that. Okay. Right, because I and j, they still exist in the local context. I don't know if all languages are like that, but since I've set I in a loop, right, it's still there. So what's the run in space? So there's one optimization we're going to make, so hold your horses if you already see it. But let's say n is the length of nums 1, and m is the length of nums 2. Well, for time, we create this default dict that's constant time. We look at all n numbers, and for all n numbers, we look at all m numbers, and then we do constant operations to, populate this array. So that's n operations, m operations for each n operations. That's nm time. Now for space, well, for each endpoint pair, we have to make we have to save information about it. That way we can use it later to figure out optimality. So we'd say for space, that's also O of nm, right? But one thing you'll notice about this problem is, well, if you have a dynamic programming situation where everything's like only based on one thing away, right? You're probably wasting space if you use like nm space or all of the elements, multiplicities or whatever, in order to find the space, right? Because well, this is based off of what? This is based off of the previous ith number and the previous jth number. So this is based off of the I minus 1 is I from the previous iteration, right? So, and this is j minus 1 is from j's previous iteration. So if I called this instead cur, or let's call this prev, and we'll call this cur. Well, the current number at ij is 1 plus the previous iterations I, because we're doing it based on I minus 1. Okay. So basically, if it's I, then it's this iteration, so it's prev. If it's I, then it's this iteration, so it's cur. If it's I minus 1, then it's prev's iteration, so it's prev. Ugh. So this is still cur ij. Well, this would be the previous iteration, and this would be the current iteration. And then we would just return current of ij. And then after you're done, prev equals cur, right? Because in the next iteration. So this is wrong. This is going to return the wrong thing. Oh, I forgot to put a 0 here too. Man. My computer sounds like a freaking airline jet right now. Oh, I called it cur, and then I'm supposed to call it cur because I'm an idiot. Which means I need to fix it here. Which means I need to fix that there. Come on, man. And then just to make it a little bit more concise, you'll notice, well, this I, if it's I or I minus 1, it's just if it's prev or cur. So we don't even need that to reference anything, right? So that's not even important anymore, right? Because we used to have to keep track of if it was from the current iteration or the previous iteration. But now we know that because we have the prev and the cur. We got the prev and we got the cur. Oh, shoot. There you go. Oh my gosh. Guys, what is wrong with me today? Keep screwing up. There you go. 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 So what does that mean in terms of space and time? Well, now we only keep cur and we populate it with every endpoint of j. But then we don't do that for all I, because after one iteration, we reset it. So we populate it with j. We populate a default dict with j elements, and then we reset it. Then we populate with j more elements, then we reset it. So we're only using j space. We use j space, then we save that, another j space, so that's 2j space. And then we populate j space, save that, populate j space, save that. So we're only using j space, right? O of j space. And this is a constant operation. We populate it. And then maybe setting prev to cur would be, it could be if you're like copying it, it could be, m operations, but that would be 2m operation, so it's still O of n time. So it doesn't affect the time, but it makes it O of m space. Okay. That's it, guys. Pretty bad video, but most of my videos have been bad as of lately. That's why I'm trying to do more to, you know, relearn the approach of teaching appropriately.